Lalitha. I'm calling you.
Okay,
Okay.
so I will share it here. So, I have to start now. Um, I think we covered this one.
Last time.
Only that one, right?
There are four parts.
There are 4 parts, yeah. Maybe we go to 2, 3, 4, or you want to do that Mesmo part? Which you prefer?
Mesmo part is in one of the rest
Yeah,
of the three, right?
yeah. Maybe we can just go in
Which one
order.
is it?
It's 3 and 4.
3 and 4. It will be very complicated in folder 2.
No, but I think a part of this model is in Mesmo.
Okay.
So maybe we could just go in order. Okay. Then later, if you want, we can talk about Mesmo.
We just go back.
Okay. So what we saw in one is the load, PV, and waste to energy. These 3 parts. And all the cooling load is separate and treated like flexible load. Sorry. I don't know why. So for maybe we open this also. Just okay. So the first part we saw all this, the demand, PV, and waste to energy. In the demand, the cooling and non-cooling are separate because cooling can be flexible. And that cooling as flexible demand we model in the second part. That is the building thermal model. That is the part. That is also the one in Python. It's a part of Meso.
Combo data is part of method.
Yes, to run the building data, for you need the thermal model. That is part of the data, that the whole data set.
Okay.
And apart from that, there is EV data. Because in EV we can have like a flexible EV type in Mesmo. So we have for SIT, JTC, the car park simulation data. 2 types of data. 2 different things: cooling and EV.
Okay.
These 2 are in part 2 because they both are flexible.
Sorry. Data 1 2 3 4. Why do you classify the data set into 4 parts?
The first part is all the non-controllable ones.
Okay.
Except waste to energy, which but it depends on the waste to energy. But and all the flexible ones come under part 2. Third and fourth are more system level.
Okay.
So the second part is the flexible ones. That's why
Flexible one includes EV
and cooling.
But air storage can also be flexible.
Yes, but for energy storage, the model is quite standard. So there is also a model in that we use, but explicitly we model only the cooling and EV
Okay.
in this one. For battery, we use the standard modeling.
Okay.
And yeah, so in the data set, that is what you will find in part 2. You will have the thermal model and the car park. Yeah, it's all together in the zip file. And this is the modeling report. Yeah, we can go through this one, then you will understand better. Let me open again. I'll open on my local folder because everything is zip file here. It contains many things.
Oh, this is
the model report. So this work mainly done by Tum Create. We only like contribute to something with
Okay.
yeah, it's more like it's one PhD student worked on this and Kai worked on it. So one PhD student, one research fellow. So they worked on this. Kai also not so much in this. He's more on market studies.
There's more on
Yeah, this was like the one guy's PhD, so it's part of his PhD, and he also added this report. So in this, yeah, they model like the for the EV, they build something called car park simulation. Like they will input some car park data, which they got from some open source data in Singapore.
car park data.
Like when vehicles are parked, how long they are parked, and when they leave. In Singapore, generally in Singapore.
Oh, there's the open source data.
Yeah, there is open source data. So we use that because SIT so far there's no campus. JTC no campus, so we take open source data. Then they did some clustering, all these.
I'm sure it's clustering.
Yeah, and vehicle inflow modeling. Yeah, inflow modeling is basically when vehicle arrive and how long it stays. So with that, they made a simulation along with taking the design data of SIT and JTC.
Sorry, taking the design data.
So this is the car park availability, how vehicles come and go. That is open source data. But for the SIT campus, we know like how many chargers will be there, what will be the charging power. We like the design data we know.
Okay.
So they merge these two together to like a car park simulation.
Oh, okay.
Design data is SIT data, but the rest of it is
Which means to accommodate the open source data to the SIT situation scenario. SIT scenario.
Yeah, exactly. So with that, they come up with this charging simulation. In that charging simulation, there are two ways to do it. One is keep it fixed, no control. Then what happens? Then if it's
stand instead of sitting.
what?
Sitting for a long time.
Okay. And if it is flexible, then how it can be unidirectional, bidirectional, both flexibilities. They try to simulate how the charging curve look like.
This is a huge amount of work.
Yeah, this is the guy's PhD basically.
Okay, yeah, so
Yeah.
merge two data sets together, and based on that, you have to extract the flexibility from the EV.
Yeah, if there is control, then how the charging curve can look like. Yeah, extract flexibility.
So based on what kind of criteria to estimate the flexibility of, I don't know, do you have this?
Uh,
There are some criteria or standard or algorithm or something.
yeah, there is. Yeah. So yeah, these are the data I explained to you. So the car park data they take from LTA data mall. This is open source, and for PDD it is the data from SIT and GTC. They combine these two. Yeah. Um, and for SIT, this is the data that we collected. The type of charger, so there are different types: slow, medium, fast. Char Slow, medium, fast, and their power rating and how many are installed. That is based on what data we collected from the campus design.
Okay, so am I right that this is a very initial this is very initial data that was collected by LTA. I guess with the increase of the EV charging station deployed in Singapore, such kind of feature of of EV data when you come in and how long you stay here will be changed slightly.
So actually here what they use the LTA data, it's for any vehicle. They didn't take the EV data.
Okay.
It's for any vehicle because the behavior will be the same. If it's EV or not EV, people will still do the same thing, right? So they take only that data, and for in the data we have different scenario like 2030. What can happen when there's 50% EV traffic, when there's 70% EV traffic? Like these are different assumption we do.
The behavior is the same.
Behavior, user behavior.
User behavior is the same, which means whatever whether you're using EV or just use a conventional vehicle,
Yeah.
the user behavior are the same.
Yeah,
Oh, that makes true. Yeah, that makes sense. That
Yeah.
makes sense.
That's the assumption. That's how they use this data for that. And this number of chargers and all is coming from the design of SIT campus.
I'm wondering how the two data are merged.
It's not merged, but it's just the simulation uses the availability information from open source data and to simulate it in one car park.
Mhm.
In LTA data also there are multiple car parks.
Okay.
So it's like as if it is one car.
So maybe we can go to see what is happening afterwards.
Yeah. So yeah, so they just simulated. I'll zoom in. Yeah, they just simulate randomly, like with that availability data, different time series. And what else?
Thanks so much.
Yeah, I think this part you will need to. Okay. That is for the electric vehicle, and for the thermal part, this is how it's done. So, so the building geometry. You remember last time for estimating demand PV and all that, we use like a shape drawings and 3D model. From that, they take the building geometry, zoning, zone types, and then the weather data that we use. They take all this as input, and then there is they use these models in the that mesmo environment. to compute like so you remember like every place it can have either library or office or like different zones. So depending on the zone type and constraints, so they define it here, and the weather type, all these inputs will go to this COBMO model. COBMO is control oriented building model.
Okay, so the input of combo model have three parts, one, two, three, four. And if you have to use all of this information plus some processing to generate the four inputs, and then go to the combo.
Yes.
And this is the output of the
of the combo.
and a combo is combo is part of Massimo.
Yes, it is the thermal part of Massimo. The rest of it is electrical.
This is okay. So combo is the thermal part of Massimo.
Yeah. It model only the cooling, right? Cooling or thermal model of the building.
Okay.
And from this model, these information, state space constraints, decisions, they will go to the system optimization.
And these are the inputs.
System optimization for next level. Yeah. So. It's the same information that I showed you in the first project, but it's after processing. Those are the inputs to the COBMO. So the format is different, the processing is different.
Okay, and the Python code for processing or processing is in our.
No, I think we did not have.
We don't have this one.
We don't have this one, but for the COBMO, we can have that. The COBMO part, you have the scripts.
Okay, so in the Python code.
So this data I give you in the first part. It's the same data. The building geometry, building zoning, zone type, everything. So last time we discussed is the same. This data I will give you. This format I will give you. But how we don't have a code for this. We did not do it using.
We
just did it with parallelly with time. We build data in this format separately. We'll build data in this format separately while processing. Yeah. So this part we won't have, but this script is available. Then using that you can generate this one for this.
Okay, so I think it would be better to me, maybe it would be better to understand what is happening, at least the concept of generating final models from the four inputs.
So I think what you need. So how these values, how they do it is. These are the ones that I showed you. Like these are raw data. Then later you process them. This is the COBMO concept. So they.
COBMO concept.
We push it a bit.
It's very complicated.
It has many inputs, like all these are coming from the data side. So solar irradiation. You have a general solar irradiation from the weather data, but you need to take it for each window. Depending on the direction, the irradiation can be different, right? So COBMO, like converts that general weather data to each building, each surface, depending on the direction, the irradiation, it will convert.
Okay, for that part, that kind of thing the will need the PV.
No, this is not related to PV. It's just to estimate
The building shape and
yeah. But the building shape and everything, we take the input from the first project directly into this, and they.
electrical guy is a thermal guy.
Yes, yeah, he's and yeah, that is it's not for this purpose of this is not for PV, but to understand how much will be the heat loss in each room or surface. When the irradiation is more, then there is more heat loss, and you have to your cooling load will increase. So like that, and yeah, and there's also information on the occupancy with time, that one. And I think appliance we didn't model. Like appliance also generates some heat, but for us we didn't model that. I think mainly occupancy and weather, yeah, and the building model itself. It will take those as inputs, and with that.
Can I understand the objective of cooling system is to maintain the temperature of this indoor area.
Yeah.
So if you increase the interaction between the indoor and the outside environment, your your load of cooling system will be increased.
Yes. Yeah.
Okay.
And the more heat loss you have, yeah, with that they try to cooling load will increase.
Okay, understand.
Yeah. Yeah, so the result is if you don't control anything, this will be the cooling demand based on the building design. This is also the one I showed you in project 1. And with control, what happens? That is the most interesting. So here we need to estimate the flexibility from that cooling, right? What flexibility we can get from the cooling. That is the objective of this one.
Yes. My question here is if you want to use a cooling system to provide flexibility, which means you have to satisfy some performance of cooling system.
Yes, yeah.
So what is the satisfied performance?
There is like a range of, there are some constraints. I think you will have.
It's also an optimization thing.
Yes, yeah. It will have some constraints in the modeling part. Like for example, I'm sure they model definitely some constraints. Somewhere in the report you should have the numbers. Or I'll directly give you the Python script. It's basically a temperature range, I think. I mean max temperature range, and they have some airflow parameter they have to meet. Those are the constraints.
Totally out of scope.
Yes, quite different. Yeah, but in the end, the point of the project is to compute how much flexibility we can get. And for that, what we try to do, like define like a matrix, how much of load shifting we can do. If we want to shift the load by half an hour, then how much of reduction we can make. If we want to shift by 1 hour, what will be the reduction in load? So like that, if you want to shift it with time, then how much load it's possible to reduce. So with that metrics, yeah, that's how we compute the flexibility.
Average load
Load
reduction.
reduction. The load here means cooling load.
Cooling load, yeah. And with if you want to shift for a longer time, obviously your ability to reduce the load will be less.
Shift means
Means you either prepone or postpone.
okay. So for the half an hour, for the half an hour, 0.5 an hour, you can only shift your load postpone for the postponed half an hour and the prepone half.
Yeah, if you want to do half an hour shifting, then what is the maximum load you can come down? Like you're doing peak shaving or something like that, for example, and you want to shift the load for half an hour, then how much you can reduce? Maximum, that is this maximum load reduction. Yeah, if so how they do it here is like suppose morning is a peak load period, then they will like pre-cool the building uh, before some time during the low price period. So that pre-cool building will last only for half some time, right? The longer you want to shift, less effective it is. Yeah, because no thermal storage here.
Okay.
Like you pre-cool the building, then after some time there will be thermal loss. Then you will not meet anymore your constraint. So yeah, you can't shift for a longer time. If you want to shift for a longer time, you need a thermal storage along with the cooling plan.
Yeah.
So here in this case, no thermal storage. That's why shorter time you can reduce more, and like longer time is not effective. Yeah. Yeah, this is the building wise load reduction for each building. Yeah, and the next parts maybe not that much useful to you because it's the UI. So they wanted to develop a UI, which one of the guys is still working on it. It's not complete still. It's still they're still working on that.
So the final deliverable will be reviewed by Edge committee.
Oh no, it's not. We have like a regular review process. So each year we submit all the deliverables. Mm. Yeah, so this part may be not that interesting for you. It's all, but maybe with this you will have more charts. Mm. This is building wise cooling curve, like JTC Tower 2, V6. That.
Okay.
Building wise. What I show you in at first is the total, and this is building wise all the information. Yeah.
How many buildings are there? 6 buildings.
Oh no, more than that. Just SIT has like 12 or 15, I think. Okay. That is the second part. These two, all the information are here. Then the third part, you have third part is where like with Soki we can share all the MESMO data with you.
So what is the code? Where is the code?
It's so here this is the data set. The MESMO code is just open source. You can download it.
Yeah, and the code Sogi is using is
that is DRO. So that one I put it under 4.
okay.
This is the extra code that
DRO distribution.
Inside this, you will have deterministic, you will have stochastic also. It's just named like that. Let me rename it so that it's clear. But this one, I don't think CNRS asks you, but let me just put it optimization or Primo optimization. Yeah. Inside it, you will have three optimization. One is deterministic, without stochastic, and then the DRO special one. And the data set to run this, what we are doing, that I put it in three. You will have SIT data set. I think this one, finally, I will, after we do all the run with Soki, I will finally upload it once again.
Okay.
SIT, there's SIT dataset, JTC dataset is separate. I'll ask her to upload also.
So what if we want to share the data with the class partner? This is the data set we can.
Yes, yeah, and I'll open that now to show you. Okay. Hey, where's my mouse? Okay.
Oh yeah, one more thing, the scripting of Python. Power factory scripting.
Yeah, okay. That's also, I also put it there. I put it in this Power Factory Python repo. It has all the script to run the quasi-dynamic.
Or you just use Python to call Power Factory model, run quasi-dynamic or something.
Yeah,
in
yeah.
a unit command.
Yeah, yeah. Okay, so now maybe I show you this tree. Okay, Power Factory Python. In that, I put all the, you will have Mess Primo Power Factory interface. In that, you will have all the file to run quasi-dynamic, run load flow. But the thing is, I think you have to modify the model. It's the same format, but when using it on another system, you have to modify something.
Okay, so I think we can put this one aside for now, and later on we can find a time to run the Python.
We'll see. Only next week.
Okay.
Yeah, yeah. Okay, and this is the whole of Mesmo the repository. This you can clone from the GitLab. I show you.
Oh, okay.
You can directly clone, or you can use this also. This also I put it in the file.
Okay.
In this one, I put it in Python Power Factory repo. Okay, and yeah, what else? We did some decision tree optimization and transactive management.
These two, I think these two are developed by Junkai, right?
No. These are developed by some interns who work with me. Yeah. The one developed by Jankai is DRO.
Okay.
This stochastic part. But in this one, you will find deterministic also. Then you will find stochastic and DRO.
Deterministic is the modeling. Deterministic optimization is developed by our own.
Yeah. Actually, this is more like joint work. But he is an expert in this DRO, Jankai.
So maybe we can go for
Yeah.
part 3.
Yeah, we'll go part 3, and I show you this one. Okay, because this is the one that they're asking you now. Okay.
Yeah, and before that, I got two questions like decision tree optimization and transactive management optimization.
Yeah.
This is there any paper or something or codes inside there?
Yeah, there's code inside that, like one conference paper or something like that.
Oh, you wrote it.
Yeah. Intern wrote it, and one guy from SIT who also work on it. three, let me see. Yeah, transactive EMS. Okay, for transactive EMS, you will have all the price analysis that they did. They did for 10 years price analysis. It was also a part of the project to do some cost analysis. So, yeah. And some multi-object. Yeah, this is also inside that folder. And this is some programs you have to.
This Python code.
It's a Python code to run decision tree.
What's the main function?
This one only. This is the folder NSGA test, I think, and generate PD. These are the two files. Okay. Yeah, this is working. That's why. Yeah. Yeah. So I think combining with this, we wrote some paper with the intern. So he put some references. Then and then there is transactive management. This one I show you. Objective, decision tree. Yeah, I think.
For transactive normalization, which one is the main? Which one is the main?
I think, yeah, I think this is my local folder, right? But I think it's multi-objective. I put this one inside transactive management. It's the same thing, multi-objective.
Multi-objective is what kind of objective? How many objectives?
I think that time. Let me recall what it is.
Between.
Yeah, between some opposite objectives. One is definitely the energy cost, and the other.
Cost.
I think the battery size, if I'm right.
You have paper waiting. You have a paper working on. You have a conference paper working on this topic, maybe.
Yes, yeah, I think it just this particular one it didn't get accepted. Then we combine it with another work and to present it. So that's why I don't have.
Is a conference paper or
Is a conference paper.
Conference paper got rejected.
Not rejected, or I think Roma reviewed it and then we didn't go through with the submission yet. Yeah, rejected internally. I think, yeah, Roma is quite strict in that. I think it's the battery size. Is the between the sizing and the energy cost that you can save. Because the bigger the battery, you can have more savings, but you also do want to have a bigger battery size. So I think, yeah, it's that one. So we combine with another work from SIT to write that. I'll put that paper in the folder later. Okay. Yeah, and even we did, oh, maybe I forgot something. I have to include a battery sizing part. In 1 and 2, you don't have battery, right? So battery sizing we did in the third part. So yeah, it's an optimization for battery sizing. I'll put the files later from here in a different folder.
This is your local.
This is my local. Yeah, I will make it and then put the zip file over there. Okay. Okay. Now we go back. Oh, yeah, yeah. SIT. Great. This. So here, you will have all these files. So the COBMO data is all the data that is linked to that terminal.
Mhm.
COBMO, we just saw. Okay. So, so you have different buildings, W1, W3, you see.
SIPJTC.
All the buildings in SITJTC. And for the buildings are defined here.
What is T? E is east, west, W
West.
is west, T is
Tower.
okay. Oh, GTC is tower one.
JTC is fully tower and podium. Yeah.
Okay.
Okay. So you define the building here, and this is in the format to run in Mesmo. Okay. And constraint schedule is, yeah, for each type of building you give a set of constraint, maximum, minimum. I think this is what you were asking me, right? You were asking for the constraints, right, in the model.
I don't think so. I think what Bundra is asking is the physical model, thermodynamic model for
That is this. That is this. This is not the only file, right? Because you have a lot of files. This is the physical model. Like you give the different surfaces and all the parameters for thermal parameters for each surface. So you see, for example, let me open something. So this is the physical model. Like for each building, you have different surfaces, east, west, and all that. Then you define in the other files the thermal parameter for each of that. So it is all we have.
Okay, so this is Excel file. In this folder, how we can I think there should be somewhere to compile all of these files together and then come together as a somehow model.
Uh, no, we use the Mesmo environment.
Oh,
And
okay.
the Mesmo requires files in this format.
Okay. So all of these Excel files
Can run in Mesmo.
Okay.
Yes, can run. You need to input it in Mesmo.
All right. So basically, I think Bourgeois is asking this input profiles.
Yeah.
Then he will use Mesmo to generate a building environment simulation environment.
But that's already done in Primo. That's why I think you have to find out what they will do. Because we did this, right? Soki is running. We already do this. So what are they going to do? I think that's for you to find. Because just running in Mesmo, yes, it's something we already did.
Yeah. So I think from his proposition, he focused on he just need an environment first.
Okay.
So
Yeah.
so based on the environment, he may develop some algorithms to control the system. Control the system.
Okay.
So,
Okay.
but to my understanding, I think what they are doing is very similar to Dream project. I mean, like generate set point of each asset.
Mm.
This is very similar.
Yeah,
This is
yeah.
very
I think
similar
that's
to
why like you
computation.
need to be like very clear with them because we give them the input data. We are giving them the environment also. And we are almost giving them everything. So what they are going to do,
Yeah.
that we should make sure that, yeah, I think
Okay, so
we do something extra. Okay. Yeah. So this data set will run in Mesmo. Yeah. I mean, later I can ask Soki. Yeah, they just use Mesmo to run this. It's already done.
Oh,
But if they're going to develop further on Mesmo or using that, then that is okay. I think they need to because they need to do something on AI, right?
yes, yes, yes.
So they need to like
I think the idea, Bundo's idea is to have the environment first, and then I can develop some algorithm, AI, I don't know, AI agent to interact with art.
okay,
Then
okay, okay.
his objective is to train AI to be smart enough to control the system.
Okay.
This is his objective, and even 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 he's doing this. Even if he's doing this, the work here is very similar to Dream 2.
Okay. I see.
Yeah, the only difference is between only difference between Dream 2 and DPS is you are using a different environment. That's all.
Yes, yeah. In fact, when do you go switch from this kind of optimization or model to AI? When do you shift?
When do I shift?
When is AI really needed? Because I think the main question of Edward, I think why he wants to know what they will do is because he want to see like some problem that in Primo or in something else that we don't solve, and we need AI to do that, something like that. But I don't know.
This is a question I don't know. This is a
Yeah,
question
I think that's what he has in mind. Like we cannot do something with normal stuff, so we go for AI.
Yeah, yeah. So the idea here is that I think most of problem can be solved by MILP, typical optimization problem.
Yeah.
So I my question here is okay. My problem, my idea is to my idea is that if you are when you are doing the optimization, so there's no chance to include the dynamics or shorten dynamics or the stability stability margin or damping ratio of the system. You don't have this kind of information in your optimization. Then you can use AI to 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 include your damping constraint in your optimization. This is what I think how we need why we need AI. But here, but I don't see the reason. I don't see enough motivation in Bondur's proposition or in Blake's team. I don't see the reason. I don't buy their way of using AI. They're just repeating. They just use AI.
Okay, yeah, just for the sake
They
of
just use AI. They just use
instead of
AI.
doing by method one, you do by method two.
Yeah,
Same thing. Like
it's the same thing. Yeah, I also
yeah, I think
so this but however I can't force them to follow my idea
yeah, okay.
because they don't get money from EDF.
Yes.
So this kind of things has to be agreed from a high level
Mm,
between Valaki and CNR's director.
mm, yeah, that's true.
Um,
Okay. But
I think it's really strange, you know. I had a discussion, I had a meeting with Blaze. He wants to know what kind of problem you have, and I can use some algorithm to solve your problem. However, you always ask me how to solve this, how to model this, how to blah blah blah, how to then of course I know how to solve the problem. Then what's your value? What kind of extra things you can do
but when is AI really like useful? Like, is it because it's a large data to process, something like that, or
that is the that
when
is the
when you have like missing things in the data? I don't know when does like is AI really like useful? Like because here I think the only trouble we face is it it takes like forever for us to run sometimes because uh, for like since each building has the model, each surface has the model, so to even run one campus simulation, it takes us very long to run. I think that is one
Very
problem,
long,
computational
very
problem.
long to solve the
Solve the
problem.
problem.
Solve the problem.
Okay.
Yes, that is the problem, but that's like a computational problem that we have.
Okay,
Okay,
so
so
maybe
maybe
the
the
question
question
here
here
is
is
we
we
have
have
this
this
problem.
problem.
It's
It's
But even
it's
AI
long.
takes long, right?
AI
AI
takes a
takes a
long
long
time
time
to
to
do the
do the
training,
training,
but in
but in
real time
real-time
operation, it
operation,
will
it
be
will be
very
very
fast.
fast.
After
After
training, it
training,
will
it
be
will
very
be very
fast to
fast
get
to
the
get the
results.
results.
Okay, okay.
One
One
second or
second
two
or two
seconds to
seconds to
get the
get the
results.
results.
It's
It's
very
very
fast
fast
after
Yeah.
after
your
your
training.
training.
Yeah, that could be something to
So
So
yeah,
yeah,
that's
that's
why.
to
why
think, but yeah.
That's
that's
why I
why I
think.
think
Okay,
okay.
so
So
And if you make any modification in the model, does it have to
retrain the
retrain the
system.
system.
retrain the system?
So
So
And you need data to train the system.
yeah,
yeah,
to
you to
train
train
system.
system.
So
So
that's why
that's why
in most of
in most
cases,
of cases,
if you want to
if
apply
you want
AI
to apply AI
power
in your
system,
power
you have
system, you have
two
two
things.
things.
One
One
is
is
offline
offline
training.
training.
This
This
offline
offline
training
training is not real.
it's not really
It's not real
offline.
offline. It's
It's
a
let's say
let's say
the
the
offline
offline
data
data
set is
set is
updated
updated
per
per
month
month
every
every
month.
month.
Then
Then
you
you
can
can
use
use
the
the
entire
entire
month
month
to
to
retrain
retrain
your
your
AI
AI
agent.
agent.
And
Oh,
And
after
after
training,
training,
you
you
just
just
directly
directly
deploy
deploy
AI
AI
agent
agent
online.
online.
And
And
for
for
online
online
real
real
time
time
for
for
online real
online real
time
time
decision
decision
making, it's
making, it's
very
very
fast.
fast.
But
But
you
you
can
can
use
use
but
but
for
for
the
the
offline
offline
data
data
set, you
set, you
can
can
use
use
1 month
1 month
to
to
retrain
retrain
data.
data.
okay.
So
Okay.
It's
it's
a
a
updated
updated
every
every
month
month
or
or
Okay.
every week.
this
Mm,
This
is
is
doable.
doable.
okay. Okay. Yeah. Maybe looking from real time perspective, it could be something,
Mm.
some value to add.
Mm.
This
And
is
this
the
is the
value
value
of
of
using
using
reinforcement
reinforcement
learning
learning
to
to
Okay.
solve
solve
the
the
optimization
optimization
problem.
problem.
Okay.
Mm.
And if like and it depends like on the, like how to say, the if you don't have proper data, you cannot.
Yes, right.
Yes, right. So you're
You're
talking
talking about
about
it
it
takes
takes
very
very
long to
long to
solve the
solve the
problem.
problem.
It
It
is
is a
optimization. It
optimization.
is a
It is a
PR
PR
optimization or
optimization or
something.
something.
Yes, yeah. Stochastic, yeah, is a
Stochastic
Stochastic
problem.
is
also.
Deterministic is okay.
Okay.
If you consider like no forecast error, then I think it's okay.
Mm.
Yeah, but like if you want to like you can also like what you can do. So this is a simple data for at least for deterministic, it's quite simple data, I think. If you can add like uh, more information on market. Here we take energy and reserve, only two and two prices. And but you can have different options, can make it more complicated. Then maybe you will see the value of a, I don't know.
Yeah.
Yeah.
If you compare mathematical and AI, I think that's the only difference, right?
Mm.
Mathematical.
Mathematical.
Like mathematical optimization. In modeling, so here you will do AI optimization or AI modeling.
AI
AI
optimization.
optimization.
Okay,
But
but AI can also be used to model, right?
Yes.
Yes,
So
so
AI is
AI is
very
very
generic. You
generic.
can
You can
use it.
use it.
You
You
can
can
use
use
you
okay.
you
You
can
can
use
use
AI.
AI.
You
You
can
can
use
use
AI
AI
to
to
represent
represent
the
the
modeling.
modeling.
This is one way of using AI. Another one is to use AI, use reinforcement learning as a solver to solve the optimization problem.
For optimization, it's reinforcement learning.
Yeah, it's reinforcement learning. And for the modeling, it can be very normal, ordinary neural network.
Oh, okay. Maybe that's also an option. Here you have like Cobmo or something like that. You can have an AI model.
Interact with
Yeah.
the Cosmo and get some results.
Mm.
And we expect that if you have AI utilized in a real-time way, the the optimal decision can be found in very fast.
Yes. Yeah.
Okay,
True.
okay. So for
It can
now,
also be like a market model, which is not here at all. In market block, we only have take the price, energy price, maximum reserve price, but it there are other market elements, right? Different schemes are there. There are different so many things are there.
okay. Yeah. So for now, how long it takes to solve the problem?
For deterministic, like a few minutes, it takes for stochastic. I have to ask Soki, but for DRO, I think when you include all the data, it doesn't solve like one day. Yeah, she's running like overnight and all that. It keeps just running. That's why we are not able to get results for this.
So for
Solver, we use a free solver called HIGHS, HIGHS. It's free. And yeah, with Tum Create, we try Gurubi, but even there, same problem.
it takes long.
Very long to solve.
HIG.
GHS, HIGHS.
Or high performance parallel linear optimization software.
It's free. Yeah. We use that at our office, and to create also try the Gurubi.
Because they have license.
Yeah.
License. Okay.
Yeah, so either with stochastic we have some time issue, then the other is
My question is, when you are doing the stochastic thing, is two stage or one stage?
two stage.
First stage is what is the objective of first stage?
Mm, so we have like actually it's three stages to be very particular. I think if how to say it's the first stage is we include like the uncertainties where like of price mainly, and yeah, for now we include just price uncertainty.
And there's no uncertainty from renewal.
We don't model those things for now.
For the first stage, we include
Price uncertainty, so it's like a market process how it happens. First stage we include price uncertainties, then after arriving at the decision, we submit the bidding. Then once the market process is cleared, dispatched, there, let me show you some picture then better to explain.
Oh, we have already finished.
No, we didn't finish the data. Are you hungry?
Maybe we can, yeah, after going through this DRO, we can go for lunch. I guess not.
I ate already.
Oh, yeah.
I didn't have lunch, but I bought something from the bakery to eat. But if you're hungry,
No, I'm not prepared.
Yeah. So our process, yeah, it's like this. So we have input of price forecast, the load and renewables, whatever. And after optimization with the uncertainties, we get the final offer or dispatch.
This is day ahead, 24 hours.
Yes, yeah, we run 1 day period.
Wait, this is the first stage. All right.
Yeah, then once we know after the market clears the bidding, we remove all the uncertainty. Now it becomes a deterministic problem.
Okay.
Yeah.
It comes to the second stage.
It comes to a second stage. And second stage, we take two conditions into account. Since reserves are involved, if their reserves may be activated, it may not be activated in that time. So we including those two conditions. So it's the second stage.
So the second stage is the second stage. It's really weird if you when you are doing the first stage, you have to consider the second stage as the stochastic thing. As when you are doing the when you are doing the first stage optimization, you also need to consider the possibility if your frequency regulation service is activated or not.
Yes. Yeah.
Right.
Yes. Yeah.
It's a okay. I think the second stage is embedded in the first stage.
Yes. Yeah.
They are not.
That's correct. It's not. Yeah. It's linked.
Oh, yeah, it's linked. Okay.
But the second part is totally deterministic. Means we don't model any distribution or anything. In this part, in the second stage, there's no probability distribution.
There's no probability.
We don't consider uncertainties.
Yeah, we were doing here. The uncertainty has removed.
Yeah.
The price uncertainty after market clear, after market clearing, the uncertainty of price has gone.
Yeah.
And what about the uncertainty of DG?
Yeah, all uncertainties we remove.
All uncertainty removed. And for second stage, you have to model the possibility of a call for frequency regulation or not call for regulation. There are only two distribution, two choices.
Yes.
So what is the possibility of being called and what is the probability of being not called?
That we didn't model, that we didn't take into account. We just make sure that in both cases we are able to control the DER.
Or the worst case.
Yeah.
Okay.
If it's called, we should be able to control the DER. If it's not called, we should also be able to control the DER.
However, if you are really
like a constraint.
Okay, if you are really called, if you are really called by PSO, then which means you don't have enough energy or storage.
No, that should not happen because it's included as part of constraint. You like the power balance is done like two constraints, power balance constraint. One is with the reserve activated, one is without reserve activated. And in two cases, you will have two different dispatch for DERs.
Okay.
Like normally you have one power balance constraint.
Right? So it's in the same optimization parameter.
Yes, yeah.
Okay.
Normally you will have one power balance constraint and you will have one set of control variables for DERs.
Okay.
DERs or flexible load or whatever.
Okay.
Here you will have two. One is with the reserve and one is without reserve.
but you have the possibility of the two.
If any one happen, we must be able to control the
To the
otherwise we
DR.
cannot participate as
DR is the distributed energy storage.
yeah, energy resource.
Really resources, and this DR include PV.
In PV we are not controlling here, waste to energy and cooling and EV.
Oh, okay. Oh, D as
And
main.
battery.
Okay.
Main thing.
You use you didn't in this case you didn't use energy storage to
Yes.
control. Okay, you only use cooling and EV.
We use battery is also modeled.
Battery is also modeled to provide flexibility.
Yeah.
Okay.
Now maybe
Maybe later on I can go through more detail.
I think we are almost there. Just is mainly the data set. So this is the COBMO data. Then for EV, there is another separate data that you have to include. So for EV, we have another data here. Then let me come back. So here, so this is all the grid system data. This is EV data, this is cooling data separately given, and this is all the system data. For the I'll start from the basic file. So you have a file called scenario in every data set. So this would be the scenario name.
The CFV file.
Yeah.
Oh.
You will have a scenario name. So this is the one that you should give in Mesmo to be able to run this. You should copy this data set and you should call this scenario name. And here you will have different things, like you can give some time step to start if you want to run one day. So time step start, end, you can give 1 day or 1 year, whatever you are doing, and the step time. And then you have some you can give like some price sensitivities, and you can import a price file. So here we use Primo price file. If you're changing some price data, you can import it. And the next is electric grid.
Okay, all of these are the data set for Mesmo.
Yes. And
includes thermal.
Include
EV thermal and
EV thermal and all the grid transformers, lines, nodes. In DERs, what you can do. Okay, so you have fixed load. You have EV, fixed generator, flexible generator, battery, flexible building. Flexible building is the cooling part. Okay, so these are all the DRs that we have in the model. So, and for each of these, the model will be defined here in the DER model file. Which model we are taking. This is the link to all the files. Because it's in CSV, it's hard for you to see. But here you will have the definition type, definition name. And the definition name will give you some name where you have to find the model. You will have the schedules. Yeah. Maybe we can do maybe what else? For you, is it like more or less clear now? Like
I think it's
the data
in
set.
this area before, but I didn't use this data set before, so
Yeah,
so it
that's
takes time
hard to
yeah, it
understand.
takes
Yeah.
time to understand it.
Mm. But normally, if you copy this and you have to run it in Mesmo, it should be
Oh, so he
okay.
so he knows how to run on this data set.
Yes, yeah. Maybe what we can do, we ask her to demo you.
Yeah, sure.
Okay. How to include this in Mesmo?
Mm.
Uh, yeah, maybe what you can do is you can clone that Mesmo. Yeah, can you clone this one? Um,
Oh, it's developed by MIT.
yeah, it's open source. Yeah, it's not. Tomb Create is working on this, but it's I think developed by a lot of institution together, mainly MIT. I think. Okay. So yeah, you have to like
Yeah.
clone this one, and then you will have to put the folder, copy that folder in this data, in the data
Which
folder.
means replace the original data.
You don't have to replace, you just add it, it should be okay. You just copy that folder here, maybe in examples. You will already have some standard. And you copy the SIT or JTC one here. And then to run, you can either run the inbuilt program scripts, or if you want, you can run the Primo script.
Okay. What kind of organization it is used here?
This one they have an inbuilt one. They have
It's a stochastic one or?
no deterministic one. They have a nominal power flow that they can run, and Mesmo under this. Examples. Yeah, you can either run this one for power flow or this one for optimization. This they are inbuilt scripts. Apart from this, you have the Primo script. Okay, yeah, these are all their inbuilt functions.
Validation, linear thermal rate, linear electric rate. Okay. Okay.
Why you laugh? Because I'm sleepy. You're sleepy too.
Oh yeah, a little bit.
Yeah,
Okay, yeah, I think,
this will.
okay. I think this probably, if I got some question, I can ask Sophie.
Yes, yeah, she is very familiar with
Okay,
this.
okay, sure. So maybe we can uh, go to the RO part 4.
Okay.
We've already finished the part 3.
Yes, part 3 is all this data and everything. In the DRO part is the Primo script.
Oh, so for now, Sogi is working on part 3 and part 4.
Yes. Um,
Eh? Am I right? Am I right that deterministic model, deterministic optimization is based on Maslow?
in Mesmo, they do optimization only for energy.
But you also have thermal model, no?
Thermal model, yes,
Yeah,
yes, yeah.
electrical and thermal
Electrical thermal, and you optimize energy and reserve.
energy reserve.
This you may not find in Mesmo. It is only in the Primo script you have energy and reserve.
Okay.
The reserve this energy reserve optimization is not done in the by the inbuilt Mesmo solver.
Okay. So Maslow is not directly included in the optimization problem, right?
Yes. Yeah.
Only the output of the Maslow is used by optimization, and this optimization is developed.
No, in fact, we are not using much from Mesmo. It's just the environment and the data format and everything is by Mesmo.
Then what's the relation between what's the relation between deterministic, stochastic, DRO weight and Maslow? Maslow is used in this analysis.
No. Like we have the data set and we don't run any script from Mesmo, but it's just it has this thermal model part that we use. Is the COBMO that is most valuable in Mesmo. Apart from that, like it's like our script can go do the rest of the things.
Only thermal quality is used.
Yeah.
Okay. The thermal quality is
I mean, you can still run the inbuilt programs with the data set. We first run it with the our data set with the Mesmo scripts. Then we built the Primo script.
or okay, we didn't use any optimization in Maslow
Yeah.
toolbox. We only used the
Like the
thermal
thermal
part.
Yeah. And without Mesmo, that we cannot link the thermal part to the system model.
However, if you want to include thermal part in your optimization, I feel like the output of the model of thermal the model of thermal thing should be somehow constrained.
Yes, yeah.
So what Sugi is doing now is also
It has includes thermal.
or
She's not modeling, but we take the model from that and we do the optimization.
okay.
In our DER list, we have flexible buildings, which is extracting from the thermal model.
Okay.
Mm.
Then we go for part 4.
Okay.
Um,
In the DRO, you will in the Primo scripts, you will have mainly you have all the rest of the data, and we just make some assumptions for uncertainty data.
Uncertainty data.
Data, yeah, data uncertainties to model that, and disturbances. So that is this part, but these are totally assumed data. It's nothing related to Primo, what we collected from Primo, because uncertainty is how we model, right? We don't know.
Or it's just based on some assumption. So the data is synthetic data.
Synthetic data. Yes, yeah, yeah. That's why it's better to. I think this is nothing relevant to share because we cannot validate it. It's just to help us run the.
Okay, so what is the variance of this data?
Yeah, we have like min, max, min, raw, and variance. Yeah, we generate this disturbance for the thermal model.
Ah, this is the norm.
This is flexible building, so
Flexible building
is the thermal. Like weather, for example, you can take something.
and disturbance. Disturbance is renewable PV.
No. Everything is only thermal. We didn't take PV disturbance yet.
Oh, for here we didn't consider. Okay, so for here this model didn't consider.
It's only price. Apart from price for building, we took some disturbance.
It's only price uncertainty. There's no PV output. Oh,
No, we haven't modeled it.
okay.
Yeah, because this is it's totally synthetic data. So even though we developed it, yeah, without any real data, it's not very valuable for.
It's a 1 year data.
Huh?
It's a 24-hour data.
Yeah, 24 hour.
The time resolution is half an hour or 1 hour.
Thing is, we do it one day till now, but we can have different data for weekday and weekend. So if you want to generate like the cost for 1 year, it's possible to do that. But we don't have like 1 year or 1 year of data. Possible to do that, but we don't have like 1 year of data set, and we don't run it also. We run only one day.
The optimization DRO is run day ahead.
Yeah.
And for the real time, I mean, when it comes to the real time, the second day, the real time operation, it will.
It's not like it's fixed, it has to run one day. The same program can be used for planning well before.
Okay.
I think it's quite flexible, this one, but it's not for real time. Based on how it's running, at least the stop with uncertainties, it's not for real time.
Because for real time, you don't have uncertainty.
Yeah.
All of uncertainty
has resolved.
realized.
Yeah.
So,
But you can use the deterministic. Yeah, it will.
No, you can go first.
You meet
Okay.
us so that probably we could do meta plates.
Yeah.
Sure.
You can go first.
Okay. Yeah. So for real time, we can still use deterministic if you want to use for real time. But what we imagine for Primo was more like a bidding problem. Like so it's not like real time control, not like that. But it's more like bidding for the half an hour period.
Wait, okay. So when
it's like we want to model the problem that we are submitting to the market, the bid that we are submitting to the market. We are doing optimization for that bidding.
Okay, for the bidding here, you submit the bid in you submit bid half an hour in advance, or you submit the entire 24-hour bid day ahead to the market.
You can do both. We did not define it, but till now we are doing day ahead.
Day ahead.
Yeah.
So the bid here is 24-hour bid.
Yes. Yeah.
Okay. Oh, so the case here is 24-hour bid submitted to market PSO.
Yeah. Like it will give, apart from that information, it will give how we can control the DER, if reserve is activated or not, that information.
Oh, okay. Isn't it okay, you have paper or the
What?
you have a explanation.
The only thing is the one I showed you. Yeah. The fur paper.
Pages.
No, it's Kai's paper. That is about the DRO. Put it on Teams. This one.
Okay. Okay, open it. On Teams. The only thing we have for Yao is this one.
Oh,
Yeah, what's this?
no. This one. I just show you.
Okay.
This one.
This paper is submitted to.
It's I think still under review. Yeah.
The journal is what journal it is?
I'm not sure. I was not part of this.
You are not in the author.
No. It's totally to create work. At least just the DRO part. Okay. Yeah. So where was I?
Okay.
Okay, that is this. Then you have these scripts to run. SO is stochastic optimization.
And
DRO stage 1 will give you the deterministic.
Stage 1 is deterministic.
No. The way it's written is like that because it's like a function. So the is the name of the function, but it doesn't reflect the stage 1.
It's a 30-page document, I think, that your browser or you have.
My browser. Yes.
Browser, yeah.
Yeah. So
The function.
this is the deterministic part, and this is the uncertainty part, right?
Okay, yeah.
And there is an exchange between these two, right?
Yes.
So in coding, it's written as a function, and this one will call this function.
Yes, right.
Right. So that is the stage 1. So the deterministic, it's written like stage 1, but it doesn't mean it's this. Okay. I can change the name if you want, but it's just I have to change in the program. That's why I didn't change.
Oh, okay. So this is actually
deterministic, and this bigger one will call the deterministic.
Stage 2 will call
the deterministic.
Okay. So by right.
I think I just renamed deterministic and changed it. But you have to change in the code also. And the DRO main is just a lot of plots and everything to combine.
And these two are the
this is stochastic. Yes, yeah.
Okay. All right.
So yeah.
Yeah, maybe I can go through this.
This also, yeah, Saki uses this also, but yeah, she won't know in detail, but she knows how to run
the code.
to run, have to get the results.
Okay. Okay. I think that's all.
Yeah, that's all. That's all. At least for the card, that's all.